Hello, this is module M4.5B, the second part of module M4.5 covering mirrors. Specifically, in this module we will talk about the properties of concave spherical mirrors. We will also learn how to draw ray diagrams to find out where an image is located given the location of the object and the radius of curvature. In part A, we learned a few basics of spherical mirrors. The key parts are the principal axis, the center of curvature, the focal point, and the vertex. The four types of rays that we will focus on, no pun intended, are the parallel ray, the focal ray, the central ray, and the radial ray. In this module, we will learn how to draw these rays by hand rather than depending on a simulation. Doing this is called ray tracing. We will assume that we can use the small angle approximation. That is, we will assume that there is no spherical aberration and that the principal rays that we draw will all converge at a single point where the image is formed. We will also learn how to calculate the distance and height of an object mathematically. The radial ray passes through 2 points, the center of curvature and a point on the object. Let's say that we want to find where the image of the very top of the object is. First, let's locate the center of curvature, which is not marked on this diagram. The focal point, which is marked, is halfway between the vertex, which is at the coordinate 0, 0 on this diagram, and the center of curvature. So since the focal point is at x equals 6, the center of curvature must be at x equals 12. Now we draw a straight line between the center of curvature and the object, and extend it all the way to the mirror. To determine how this ray reflects, we draw a tangent line at the point of reflection, then we draw a normal line perpendicular to the tangent. It turns out that the normal line for a radial ray is always on the radial ray itself. That is, the angle of incidence for a radial ray is always 0 degrees, because the radial ray actually just traces out a radius of the circle, and the radius of the circle is always perpendicular to the tangent of any point on the circle. So the radial ray always just reflects right back through itself, back to the point on the object, and back through the center of curvature. This makes the radial ray very easy to draw, since we can actually bypass the whole draw the tangent, draw the normal thing, and just draw the ray from the center of curvature to the object to the mirror and back. What if the object is behind the center of curvature? Well, in this case, instead of drawing from the center of curvature through the object to the mirror, you just start at the object, then go through the center of curvature, and then to the mirror. Again, since it is a radial ray, it just reflects back in the same direction. Unfortunately, despite being very easy to draw, the radial ray is not always helpful when we want to use the small angle approximation to avoid spherical aberration, because the mirror is often too short so that the radial ray never even hits it. It just continues on above or below the mirror without ever reflecting. For this reason, most people do not consider the radial ray to be a principal ray, and they don't use it when ray tracing to find the location of the image of an object. The remaining 3 principal rays are the parallel ray, the focal ray, and the central ray. These rays are very useful for determining the location of an object because they reflect from the mirror in predictable ways, making them quick and easy to draw. Unless otherwise specified, we will assume we want to find the point on the image that corresponds to the point at the very top of the object from here on out. The parallel ray is drawn from the object, parallel to the principal axis, all the way to the mirror. Properly speaking, we should then draw a line tangent to the mirror at the point of reflection, draw the normal line, and then draw the reflected ray so that theta 1 equals theta 2. However, assuming that the small angle approximation is valid, we know that any ray that is incident to the mirror parallel to the principal axis will reflect through the focal point. So we get to skip drawing the tangent and normal and just draw the reflected ray going through the focal point. The focal ray is drawn from the object, through the focal point, all the way to the mirror. Again, you could draw the tangent, the normal, and use the law of reflection to find the reflected ray. Or you could simply realize that the focal ray is taking the same path as a parallel ray, only in reverse. Since all rays incident to the mirror parallel to the principal axis reflect through the focal point, that means that all rays incident to the mirror through the focal point reflect parallel to the principal axis. So again, we get to skip the step of finding the tangent and the normal and we can just draw the focal ray going through the focal point, hitting the mirror, and reflecting back parallel to the principal axis. Don't get confused by the name of the central ray. Remember, it is the radial ray that goes through the center of curvature. The central ray is drawn from the object straight to the vertex of the mirror. If you draw the tangent and the normal, you will see that the normal line for the central ray is always just the principal axis. So again, you can skip the tangent and normal step and just draw the central ray so that the angle of incidence, measured from the principal axis, is equal to the angle of reflection, also measured from the principal axis. The radial ray is neither incident nor reflected parallel to the principal axis, and it does not depend at all on the focal point. So the radial ray is not subject to spherical aberration. If drawn perfectly, it is therefore the most reliable ray to use to find the image. However, for me, the radial ray is the hardest to draw and probably the one that I draw the least accurately. So personally, I save it for last. I know that if the small angle approximation is valid, I should aim this ray towards where the parallel ray and the focal ray intersect. Then I can check to make sure that the angle of incidence and the angle of reflection look about equal. If they don't, either one of the other rays was drawn incorrectly or my mirror violates the small angle approximation. Since for the purposes of this class we are going to assume the small angle approximation is valid unless otherwise stated, it is safe to go ahead and do it this way, drawing the focal and parallel rays first and aiming the radial ray towards their intersection, if that makes it easier for you. We can now identify the location of the image. The units of measurement have not yet been defined, so let's just say that these numbers are measured in meters. Then we can say that the location of the image is a distance of about 18 meters from the vertex of the mirror along the principal axis, or x equals 18 meters. Since distance of the object from the vertex of the mirror along the principal axis is a lot to say and to write, we can call this distance dO, or d sub O. We can also call the distance of the image from the vertex of the mirror along the principal axis di, or d sub I. We will also want to compare the height of the object with the height of the image, so we can call the height of the object HO and the height of the image HI. In the diagram that we have drawn here, with the center of curvature C at 16 meters, the focal point F at 8 meters, and the distance of the object DO at 14 meters, we find that the distance of the image is about 18 meters. The height of the object is 2 meters, and the height of the image is about 2.6 meters. However, the image is upside down, so we should really say that the height of the image is negative 2.6 meters. So we can summarize the properties of this particular diagram. DO is greater than C, DO is less than the absolute value of DI, HO is less than the absolute value of HI, the image is inverted. One other thing we can say is that unlike the image in a plane mirror, which is formed at the intersection of virtual rays, this image is formed at the intersection of real rays, so the image is a real image. But these properties change depending on the placement of the object compared to the center of curvature. There are 5 basic cases which we will go over next. Let's look at the first case when the object is far from the mirror and DO is greater than C. First, I will draw the parallel ray, then I draw the focal ray, and finally, I draw the central ray. You can draw these rays in any order, that is just the way I like to do it. We find that the distance of the image is about 17 meters and its height is about 1.5 meters. So the image is closer to the mirror than the object and smaller. The image is also real and inverted. The next case is when the object is located at the center of curvature. Again, I start with the parallel ray, then the focal ray, and finally the central ray. We find that the image is located exactly at the center of curvature as well, and it is the same height as the object. The image is also still real and inverted. The next case is when the object is located between the center of curvature and the focal point. I switched it up a bit here and drew the object upside down, but we can still use the same process. First draw the parallel ray, then the focal ray, and finally the central ray. We find that the image is located at about 18.5 meters and it is about 2.5 meters tall. the image is still real. Now, even though the image is upright on the screen, it is inverted compared to the object, so the image is still said to be inverted. The fourth case is when the object is at the focal point. We can still draw the parallel ray, and we can still draw the central ray, but the focal ray causes a problem. Drawing the focal ray from the top of the object through the focal point makes the focal ray just point straight down. If we try going through the focal point first, it just points straight up. Either way, it never reaches a mirror that is short enough to obey the small angle approximation. Could we determine the image location just by looking at the intersection of the parallel ray and the central ray? Well, that presents a problem as well, because these two rays are parallel for any object at the focal point, and if they're parallel, that means they never intersect. Since the three rays never intersect, no image is formed. The final case is when the object is located between the mirror and the focal point. First, let's draw the parallel ray, then the focal ray, and last, the central ray. But it seems like we have another problem. These rays will never converge either. But remember that for the plane mirror, we could extend the real rays behind the mirror, creating virtual rays that formed a virtual image. Let's do that here. So the image is formed by the virtual rays behind the mirror. It is larger than the object, further from the mirror than the object, it is upright, and it is formed by virtual rays and is therefore a virtual image. Ray tracing is a good way to get a quick idea of the properties of the image and to gain a conceptual understanding of why the images appear as they do. However, sometimes we want more quantitative information. There is an equation that gives precise values for the distances of the object and the image in relation to the focal point. This equation is actually called the thin lens equation because, as we will see in module M4.6, it can also help us find images formed by thin lenses. The most important thing to remember in this equation is that all three quantities, DO, DI, and F, are in the denominator, so you need to be very careful with your algebra. Let's do an example. Suppose we know that the object is located at 14 meters and the focal point is at 8 meters. I want to find the distance to the image, so I want to get 1 over DI all by itself on one side. Keep everything as a fraction for now, it'll make your life easier. This is one occasion where it is probably safer to plug in numbers before trying to get anything out of the fraction. In the end, we find that the image will be located at 18.67 meters. The problem we just did is actually the same setup we used for the very first ray tracing diagram that we did on slide 10. Back then, we identified the image as being located at approximately 18 meters. However, it seems like even with a mirror length of only 2 and a radius of curvature of 16, there is still a little bit of spherical aberration going on, and the image is actually located a bit further back at 18.67 meters. In this diagram, I included the radial ray so that you can see that the intersection of the radial ray and the central ray, the two rays that are not subject to spherical aberration, give a much better picture of the location of the image. The thin lens equation is not subject to spherical aberration, so any values you find with this equation are exactly correct. Another equation tells us about the relationship between the object and image heights and the object and image distances. The ratio of the image height to the object height is equal to negative the ratio between the image distance and the object distance. This ratio is known as the magnification, or M. If the magnification is negative, the object is inverted. Magnification greater than 1 means the image is larger than the object. Magnification of less than 1 means the image is smaller than the object. Using our values from before, negative DI over DO is equal to negative 18.67 over 14. So the magnification is negative 1.33. This means that the image is larger than the object, and the minus sign tells us that it is inverted. Since the height of the object is set to 2 meters, we can now use the equation to find HI. we find that HI is 2.67 meters, which is slightly taller than the object and negative, again agreeing with the diagram. Note that magnification is just a distance over a distance, or a height over a height, so the units cancel and magnification is unitless. This photo should now have a whole lot more meaning to you than it did the first time you saw it. The image of the hand is upright and it's larger than the actual person's hand because it is between the focal point and the mirror. The bench and the trees in the background are inverted and they're smaller than the real bench and trees because they are further from the mirror than the focal point. The mirror has a small angle of curvature, so spherical aberration is minimized with only the distant objects, the trees, being a little bit out of focus. In summary, ray diagrams for a small angle concave spherical mirror can be drawn using three principal rays: the parallel ray, the focal ray, and the central ray. The image is formed where these rays converge. The distances of the object and image from the vertex, measured along the principal axis, as well as the distance to the focal point, can be found mathematically using the thin lens equation. 1 over DO plus 1 over DI equals 1 over F. The magnification of the object is given by the equation m equals negative di over do, which equals hi over ho.